Ever struggled with getting your LLM prompts to accept structured data without writing custom validation for every field? We'll implement a FastMCP prompt that handles typed parameters like listInt and dict_str, while automatically enforcing JSON schema validation. So clients pass stringified data that converts cleanly to Python types, and your code stays type-safe. You'll see exactly how the same prompt works with both raw JSON strings from remote calls and native Python objects in direct testing.
Numbers 1, 2, 3, 4, 5. Metadata \source \API \version \1 0 \. Threshold 2.5.
This demonstrates the schema-backed prompt pattern, where LLM message templates become strongly typed components with automatic validation and dual-mode input handling. The distinctive feature is its ability to accept either native Python types or stringified JSON arguments while enforcing consistent structure through type annotations. Unlike traditional string-based prompts, this approach embeds validation rules directly in the function signature, creating self-documenting templates that work across both programmatic and networked calls. The pattern operates by treating type annotations as executable schemas that generate both validation rules and user guidance. When clients pass string arguments like 1, 2, 3 for a listInt parameter, FastMCP automatically validates the JSON structure and converts it to native types, while direct Python calls bypass serialization entirely. This creates a unified interface where the same prompt handles both numbers 1, 2, 3 from remote clients and numbers 1, 2, 3 from local code, with schema descriptions serving as the single source of truth for expected formats. The value lies in eliminating the prompt maintenance tax while preserving flexibility. Developers define templates once using simple annotations like listInt or dict_str, and FastMCP handles the conversion heavy lifting, though the docs explicitly warn against complex nested types that may not serialize reliably. This approach shines in version systems where prompts evolve independently of clients, as the schema contract ensures backward compatibility. The trade-off is disciplined type annotation, but the payoff comes in reusable, self-validating templates that work consistently across direct calls and networked requests. Let's break it down line by line. This defines a FastMCP prompt using JSON schema format, establishing a strict contract between clients and your implementation. The string values must conform to specific schemas. Numbers as a JSON array of integers, metadata as a JSON object with string values, and threshold as a numeric string that auto-converts to float. FastMCP handles basic type conversion automatically, but the docs emphasize keeping annotations simple, stick to listInt, dict_str, and primitive types for reliable behavior. This same prompt works with both string arguments from external calls and native Python types, direct invocation, with schema descriptions serving as both validation rules and user documentation.
Numbers 1, 2, 3, 4, 5.
This stores a JSON serialized list of integers as a string, enforcing FastMCP's schema contract, where string inputs must match declared types. The pattern enables dual-mode calling. Clients pass string arguments while Python code uses native types, with automatic conversion for simple annotations like listInt or dict_str. Note that while FastMCP handles basic type conversion, complex nested structures require explicit schema validation. Keep annotations simple for reliable behavior. The string representation here, 1, 2, 3, 4, 5, must strictly conform to the declared listInt schema in the prompt's type hints.
Metadata \source \API \version \10 \.
This stores metadata as a JSON encoded string, containing structured key-value pairs for source tracking and version control. The double escaping maintains valid JSON when the outer structure is parsed, while FastMCP's schema system enforces that this field must deserialize to a dict SDR. Simple type annotations like this ensure reliable conversion between string inputs from clients and native Python types for direct calls, though complex nested structures may still require explicit validation.
Threshold 2.5.
This string-encoded float establishes a numeric boundary for comparison operations, automatically converted to Python's float type by FastMCP's schema enforcement. The JSON string format ensures consistent serialization while maintaining type safety through the declared float schema in the prompt definition. This pattern enables the same prompt to accept either string arguments from API clients or native Python types direct calls, with FastMCP handling the conversion for simple types like numbers, strings, and basic collections. For reliable conversion, keep type annotations. Simple, complex nested structures may fail validation. Closing brace completes the JSON object, enforcing valid syntax for FastMCP's dual-mode input handling. This pattern allows the same prompt to accept either stringified JSON from external clients or native Python types, direct calls, with automatic conversion between them. The schema requires string values to match specific JSON structures. Numbers must be a JSON array of integers, metadata a JSON object with string values, and threshold a numeric string convertible to float. FastMCP handles basic type conversion reliably for simple annotations like listInt or dict SDR, but complex nested types may fail validation. Keep schemas straightforward for predictable behavior. FastMCP schema contract pattern. This JSON payload embodies FastMCP's strict schema-driven contract, where string inputs must validate against declared JSON schemas, while native Python calls bypass serialization. The numbers array, metadata object, and threshold value each follow specific schema rules that FastMCP enforces during conversion. Simple types like listInt and dict SDR work reliably, but complex nested structures may fail silently. Your tool's type annotations become both the validation rules and the user documentation, with the schema description serving as the only guidance clients receive about expected formats.
The interface that demands precision creates flexibility.